Hello guys, welcome back to my channel. Today we are going to be discussing the overlapping interval pattern. So the overlapping interval pattern is a very important pattern that allows us to solve problems that relate to intervals, and there are actually a couple of those kind of problems. One very popular example is a problem whereby you are given a set of ranges, represented as 2 points on a line, and then you're supposed to merge overlapping points, such that you have a single line that now represents sets of intervals that overlap, and then we now have like multiple of those lines. So let's say, for example, you are given a representation of values of this range, something like this. So you have like values of this range, this range, this range. So if you imagine that this represents one input with this start and this end, this also represents another input with this start and this end. This is another one. So you now need to sort of merge these intervals because the overlap, there's a sense of overlap between these two elements here. So you now need to merge them together into one, and then let's say there are other inputs that are represented this way. So now you need to merge this so that by the end of the merging we'll end up with this representing the first interval, this representing this single interval, this one, and then another one representing this. So initially we are probably given like an input of about 1, 2, 3, 4, 5, 6, 7. 6 values, and then at the end of the day, after merging, we end up with just 3 intervals. So you can imagine the kind of scenarios where we'll have this kind of this kind of questions. The most direct one is the merging of an interval. So imagine you're given like intervals represented as a two-dimensional array. So usually you probably will have like an integer array or a list with 2 indexes, representing one entry, start and end. And then you're supposed to merge the intervals that overlap. Another example is if you imagine like a meeting scheduling problem, whereby you're supposed to schedule a meeting to ensure that there's always a meeting room available for people who are to have a meeting, or to actually see if there is a way to schedule a meeting during a particular day for a particular person. So you imagine that one entry will now represent some meetings. The first one could be like stand-up during the day, next one could be like sprint review, Then you now need to figure out how you merge those intervals together such that there is a spot to place another meeting. Another kind of question is the question whereby it will tell you figure out how many segments you can create, from a set of lines on a Cartesian plane. So at that point, we are doing something similar. So we are trying to merge, and then we are trying to see how many intervals overlap and those that don't. So the question now is, how do we solve this kind of problem? So usually you'll be given an input that will be represented as a two-dimensional array. So let's say usually an integer array, but this time around we'll have a two-dimensional integer array such that every entry is going to be a two-dimensional integer. So the first one could be an index from 2, let's say 2 to 4. The next one could be an index from 3 to 6. The next one could be an index from 8 to 10. Another one could be an index from 1 to 5. And then actually I think we should do more. Let's say we have another input from let's say 12 to 15. And then let's say we have another one from 14 to 16, and the question says we should merge the overlapping intervals in this input. So this is the question. So it's easy to see here now that if we imagine that we create a plane, an xy plane, such that we represent every one of these inputs on a plane. So let's say this is a 0, this is a 2, this is 4, this is 6, this is 8, 10, 12, 14, and 16. And then we represent each of these range, as a line on this plane. So this is 1, representing 2, 4, first one. Next one is 3, 6. We can represent it this way. I mean, this doesn't matter. It could be up here. It could also be down here. We're not really representing anything with the y-axis, so it doesn't really make any much difference to us. But let's just put it up here. That's going to suffice for our solution. Then the next one is 8, 10. The next one is 1, 5. So 1 is maybe going to be somewhere here, all the way to 5. And the next one is 12, 15. So let's say we have 12, 15, and then another one is 14, 16. And the question says we should match overlapping interval and then return another integer array or a list that represents the merged intervals. So we can immediately see here now that this problem has reduced. In fact, looking at this, we can immediately know that the output is going to, the first interval is going to be this whole interval because they all overlap. So it's going to be something like this. So that range will be from 1 to 6. The next interval will be this one, does not overlap with anyone, which is from 8 to 10. The next one will be this one, from 12 to 16. Do you see this? So we have 1 to 6, 8 to 10, 12 to 16 as the 3 intervals. So at the end of the day, we'll be returning back a list that is represented by all of this. So the question now is, in code, how do we implement something like this? How do we match these intervals? So that's the idea of this problem. So now to solve this problem naively, ideally what we would do is you can imagine that we would process each of these entries one by one. So you could take the first entry, which is this 2, 4. Then we would move through all the other elements in the array and then try to see the ones that overlap with this 2, 4. So by the time we do that, we go through this, we realize that 2, 4 merges overlaps with 3, 6. So at the end of the day, maybe we do something like we merge them together. So we now have like a 2, 6. Then we continue to see if we can merge that with that 2, 6 with 8, 10. We cannot merge. Then we go forward again, see if we can merge that with 1, 5. It merges. So we now have like a 1. So we have a 1, 5. Then we try to merge with the next one. We try to merge. So this is 1, 5. So this will now be 1, 6. The result of this merge. So then that was not all. We also then try to continue to merging. Continue to merge with 12, 15. We cannot merge. Continue to merge with 14, 16. We cannot merge. So once we are done, that's the first iteration. Then we go on for the next iteration. We process this next element already. We already merged this, so we can choose to remove it from what we'll be processing next. Then we try to process for 8, 10. Now we try to merge 8, 10 into the next element. This has already been processed, so already been merged. So we skip that. We try to merge it into this. We cannot merge it. We try to merge it into the next one. We cannot merge it. So we have another interval as 8, 10. Then we do the same thing for 12. We try to for 12, 1. For 12, 15, we try to merge it with the next. It actually merges. Then we have then that now becomes 12, 16, and then that's it. This is now processed, and then this is also processed. So we can skip this. But you can imagine that this is actually an approach whereby for every element we go through the entire array to see if we can merge it with the previous one. So now that itself suggests that we'll be having a double for loop, and a double for loop is bad. So basically that's an n squared. At least for this particular case, this is an n squared approach, and we can do better than that. We can do far better than that. And how do we do that? Pretty simple. What we need to do is just take a little observation. If you take a little observation into this problem, we would immediately realize that imagine that we had a single line here. Imagine we had a single line here, and then this line is moving across. Yeah, so it's moving across from left to right. The first element it meets on its path is this one. So once it meets this element, this is the first range. So it picks up this range and says, okay, yeah, there's an interval that has started. We are on this interval and then we continue to move. When it moves forward again, it gets to the next range. It meets this range. Now meeting this range, and then meanwhile it's processing another range, then we perform an operation that sort of does a merge. So we merge this range into this one. Yeah, so now the result of this merge is this. So you can see, so it's almost like as if the 2-4 range is swallowed within the 1-5 range. Yeah, but the point is that we merge it. So now once we merge, the line continues. So it goes to the next line it meets is this one. Yeah, so as it merely meets this next line, we do the same thing. We merge this into this. Now this time, as we perform this merge, what happens is we end up with this. So you can see it's an extension of almost like the entire interval, and then the line continues to move. So the same thing continues to happen. The line continues to move ahead. So let's represent that. So it moves all the way to 4, moves to 5, moves to 6. By the time it's moving beyond 6, it realizes that, oh no, this interval is done, and now we have an interval of 1-6 represented here. You can see interval of 1-6. Next thing, we also do the same thing. We have an interval represented by 8-10. And then the same thing happens here. We have an interval represented by 12-16. Yeah, so if we use the idea of what I just described, we realize that actually we have an approach to solve this problem. So let me just quickly represent everything all over again. So it's 1-5, there is a 2, 4, I think there's a 3-6. Yeah, so if you get to this point, so now how do we actually now approach this? That suggests to us that, okay, what if we sort these elements? If we sort these inputs using the starting indices, yeah, if we sort all of these inputs using the starting indices, what do we end up with? If you just take a minute to think about that, that allows us to process these elements in the order of their starting index. Yeah, which is exactly what this line does. Yeah, as it moves from left to right, it picks up elements in the order of their starting index. So that means that in this entire elements now, 1-5 is processed first. Yeah, so regardless of how the input is given to us, 1-5 is processed first. So what we need to do is let's just create a copy of this guy so that we can have something to work with. Okay, so let me just erase this. Okay, so that was 12. So now we sort these elements using the starting indices. So that's the first step. Sort using starting index of range. So now once we sort using the starting index of range, what we end up with is that we'll now have 1-5. Actually, for this entire input, what we have is we have 1-5 here. It's going to, the input is exactly the same thing, just that now we have 1-5. I'm going to just erase this. Okay, so now we'll have 1-5 and then remove 1-5 from here. Yeah, so this is now our input after it has been sorted. Yeah. Okay, so now at this point we cannot process this in this order, and what we do is, imagine that we have like a single line going across. So we pick like the first element, and say, okay, yeah, so we are processing the elements within the range 1 to 5 now. Yeah, so now what we now do is move on to the next element in the next range. The expectation that the next element we are seeing definitely must be the element with the next lowest starting index, which is 2, 4. So now we pick up 2, 4, and then we ask ourselves the question: can we merge 2, 4 into this range of 1, 5? Yes, we can. Yeah, I mean, the question about if we can merge simply is, imagine that this is the ending index. Let's say this is E0. This is the starting index, this is start 0. So for every other element that we're picking, now we're picking in 2, 4. Yeah, so this is starting index 1, this is ending index 1. And we ask ourselves the question: can we merge this into this? The question about merging simply translates to, is the ending index of the starting one greater than the starting index of the first one, of the next one? Yeah, if it is, it means that we can merge this one into this one. Yeah, so now in this case we just merge. I mean, obviously you can see that there is an overlap. This 5 is greater than 2, which is easier than is S1. So we merge this into this, and then when we merge, yeah, we need to make sure that we end the entire line. Remember that when we merge this into this, yeah, the starting index of this new merge is 1, and the ending index was the end year. The end year now represented what the maximum between the two ends of the intervals that we merged. Yeah, that is a very important point. So that will mean that at this point now, when we merge this, we'll have 1 as a starting index. Obviously, what is going to be 1 since it's the one we're starting with. But then the ending index will be the maximum of E0 and E1. Yeah, so in this case now, maximum of 5 and 4 is 5. So we have 1 and 5. This is a very important point. At the end of this merge, we end up with this. Yeah, then we go on to the next element, yeah, which is 3, 6. So now we merge 3. We see, can we do the same thing? Can we merge 3, 6 into 1, 5? Yes, we can. Yeah, remember, E0, the ending index, is it greater than the starting index of the next one? It is. So we can merge. So now we merge. Remember, merge. The new interval is going to start with the initial range, and then it's going to end at what the max of the two end ranges. Very important point. So here now you can see that compared to the previous example where the ending index, the maximum was the ending index of the starting interval. In this case now, 6 is larger. So at the end of the day, the merge gives us 1, 6. So that's why this is a very important point to also note for this algorithm. So now we have a range of 1, 6. Yeah, so we have 1, 6, and then we pick the next one. The next one is 8, 10. So now picking the 8, 10, we ask the same question: is this ending index of 6 greater than the starting index of 8? It is not. Yeah, it is not. So that suggests that immediately this is done. Yeah, because we know that this is done because we had sorted all the elements based on the starting index, which means that there is no element that we have within the many ranges that are left in this our inputs. There is no range that has a starting index value that is going to be less than 8. Yeah, so and then if you are processing 8 next, that means that we are done with 3 and 6. Yeah, so we can immediately now output and say that, okay, yeah, so we have a range that is complete, and then that range is not 3 and 6. The range is 1 to 6. Yeah, then we repeat this same process for 8, 10. We do the same thing. Can we merge 8, 10 into 12 and 5? No, we can't. Yeah, because the ending index there, 10, is less than the starting index, 12. Yeah, so this becomes another interval, and then we go on to the next one, pick 12 and 15, and then we ask the next question. Processing for 12 and 15, we pick the next element, 14 and 16. Yeah, so is the ending index of 12 and 15 greater than the starting index of 14, 16? Yes, it is. It is greater than 16. So we can merge these two together. And then once we merge, what do we have? We end up with what? 12. I remember the same thing, we pick the max of the last two, and 16. So you can see at the end of the day, we end up with an output of 1, 6, 8, 10, and 12, 16. So my voice is a little bit bad. Now, if you compare this answer here with the answer we got from the naive approach, exactly the same thing, 1, 6, 8, 10, 12, 6, 10. Yeah, that's exactly what we got from the visual analysis of the ranges. Yeah, what the important difference here is that the time complexity of this problem remarkably reduced. Yeah, and the way you reduce is, first thing we did was to sort. Remember, that sorting time complexity is n log n. Yeah, the best sorting algorithm you can think of, at least for this kind of problem, for this kind of input, is n log n. So now, with that n log n process done as a sort of like a pre-processing, we have n log n. Then we now process the elements in a single linear fashion. Yeah, so we just go all the way down. We don't repeat some processes for an initial element and then now go back again to repeat the same process. No, we don't. We just go singly down. So that suggests that we now do a linear time operation. So n log n plus n, asymptotically, this translates, or this, the time complexity analysis of this is O of n log n. So which is a very significant upgrade from our initial O of n square algorithm to this new O of n log n. Yeah, and regarding space complexity, yeah, so depending on the sorting algorithm that is used, extra space might be used for sorting, but usually for this kind of problems, the sorting is done in place. Yeah, and then for the sorting being done in place, we are not using, that means we are not using any extra space. Yeah, and then the space complexity is of 1. Yeah, but depending on the programming language that you use, the sorting might require some extra space. Yeah, match sort might require extra space. We require extra space, in which case space complexity is now O of n. Yeah, but time complexity is remarkably improved. Yeah, so this is the way to solve problems related to intervals, overlapping intervals problems. Example of which includes things like meeting scheduling, interval merging, interval ranges. Yeah, for this kind of problem, this is how we want to approach it. All right, guys. Thank you once again for joining me in another session. And please don't forget to like, share, and subscribe. And see you guys again in another session where we'll be discussing the next pattern in this list, which is the modified binary search pattern. Yeah, actually, we'll start with the binary search pattern, then we'll talk about the modified binary search pattern. All right, guys. Thank you.